Hello and welcome to the channel where we're going to talk all things calculus. My name is Beth Dorsing and I'm an AP Calculus teacher who also has the privilege of reading the AP exam. So I have a lot of experience knowing how to answer free response questions and also knowing what you need to say so that you can get all the credit for all the things that you know. Each of these videos will include a free response question that is similar to what you'll find on the AP exam. I try to use similar language and cover as many concepts and get a wide variety of questions as possible so that we can prepare you for that exam. So for each video, there's some materials that you're going to need to be successful. The first is the How to Make Your AP Reader Happy document. You can print this, you can take notes in your notebook. I'm going to give you lots of tips and tricks for how to write your answer, how to justify your answer, what some of the language on the AP exam is going to need, and how to recognize certain types of questions. This is by no means comprehensive, but it is a good start, and there's going to be some good stuff that we talk about. You're also going to need access to a copy of the question. This is found in the description of the video. And then finally, you're going to need access to some sort of calculator, whether that's a TI-84 or Desmos, which is built into the exam now. I'm going to give a lot of tips on how to use Desmos, and that will be my primary calculator for any calculator active questions. All right, now that we're ready, let's get after it. Hello and welcome to the cycling problem. This is a calculator active free response question about linear motion. So you're going to need access to Desmos or a TI-84. We're going to talk about velocity, position, and acceleration and how they're related to each other. We're going to learn and review how to describe the motion of something in linear motion. That means moving left and right. We are going to kind of look at displacement, total distance traveled, and how to calculate those and kind of what the little nuanced differences are between those two types of concepts. So after we take a look at the problem and talk about how to solve each component and the scoring of each component, we're going to wrap up the video at the end with a summary, and so you'll need that How to Make My AP Reader Happy document to take a few notes on, in general, how should you approach these linear motion problems. Now, before we get going on this problem, we need to make sure we have Desmos open, and the best way to ensure that you're using a version of Desmos, most like what you're going to see on your exam, is to go to desmos.com/testing, or just Google testing Desmos and look for this page that starts with the United States. And if you just kind of scroll down, you'll see that Desmos is built into a lot of high-stakes testing. And so you're going to look for the College Board, and you're going to click on the graphing calculator for the College Board. And the nice thing is this graphing calculator is already defaulted to radian mode, which is what your calculator needs to be in for every calculator free response. There are no degrees in AP Calculus. I am going to turn mine into projector mode just so it looks a little bit bolder. That's not a step that you need to do. So let's take a look at our problem. A cyclist travels along a straight path for 120 seconds. The cyclist's velocity is modeled by the function v of t, where t is measured in seconds and v of t is measured in meters per second. Now, before I even read any of the questions, if this is calculator active, I am going to actually start by just typing in my equation into Desmos. And when I do this, I want to make sure that I am using function notation, and I'm going to type the entire function in, including the v of t equals. And you're going to see in just a little bit that this really allows me to really use Desmos to do a lot of calculations for me. There's a lot of things I can do with my TI-84, but my focus is on Desmos because Desmos, I think, is a lot easier, more readily available, and it's free for everyone, and it's also embedded in your test. So one thing that I will always do to ensure that I've typed my equation in correctly is I will always just take a moment and look at my Desmos and make sure that my equation matches what's on my paper. Take the time to do this so that, because if you don't, your calculations will be wrong. And you have the time on these calculator questions to do this, so just make sure you're doing your due diligence and putting your calculator, to good use. Okay, so part A, let's read through it. It says, find all the times in the interval from 0 to 120 at which the cyclist changes direction. Give a reason for your answer. Now, as I think about this, I need to think about, okay, when do I know that something changes direction? Well, in order for anything in motion to change direction, to turn around and go the opposite way, it has to stop first. So the first thing I'm going to look for is, do I see anywhere where the velocity is equal to 0? Now, velocity also is directional. In other words, if you have positive velocity, that means you're moving to the right or forward. If you have negative velocity, generally that means we're moving to the left or backward. So in order to really change direction, you not only need the velocity to be zero, but you need to see that you've changed sign from positive to negative or negative to positive. And the nice thing about doing this on a graphing question is that we can actually use the graph. So let's take a look at our Desmos graph. And when I zoom out, if you have a touch screen, it's actually really handy. If you need to use the plus or minus to kind of like zoom out, like those are nice too. But I find that if you can use the touch screen, you can actually pinch the y-axis and just expand the y-axis just by making sure that when you pinch, you're just pinching along the y-axis. You can do the same thing for the x-axis, and if you really need, you don't have a touch screen, you can always go to those settings and you can kind of change what you're counting by for the x and the y and just type in a new thing, a new viewing window, if you will. But I have this viewing window right here, and I can see, I have to see everything from 0 to 120, so I'm going to zoom out far enough to see everything. And then all I have to do in Desmos is tap those x-intercepts, and that's actually going to give me the two places where we have a direction change. And I see that I'm changing direction because at that 36.0 value, above the x-axis is where I'm going to have positive velocity, so I'm moving to the right. And then when I get to t equals 36, that's when I stop, I turn around, and the cyclist then moves the other direction between 36 and 108. And then at 108, we see that our velocity becomes 0 again, so that means the cyclist has stopped. And we know they've turned around and gone the other direction because now their velocity is positive. So they were going to the right, they stopped, they went to the left for a while, they stopped, they turned around and went back to the right, or forward, backward, however the motion is for the problem you're looking at. So how do we write our answer to maximize our points? All right. I'm going to record that the velocity of t equals 0 at t equals 36 and 108. I'm also going to mention that the velocity also changes sign. Therefore, the cyclist changes direction at t equals 36 and t equals 108. And that's how I'm going to write my answer. Now, if you look at the rubric will tell you that this is worth 2 points. You get a point for identifying 36 and 108, and then you get a point for saying why you know that those are the places where we change. So just simply saying they're x-intercepts is not enough. You need to say that the velocity is 0. So we want to always be referring to the problem and the equations in the problem. If you're giving general information about like an x-intercept, make sure that you're referring to v of t and saying v of t has x-intercepts at 36 and 108, but you also then need to give a second piece of information. Usually when we justify anything, 2 pieces of information is your general rule of thumb for most justifications. You need the derivative, or in this case the velocity, which is the derivative of position, to be 0, and then you need to show a sign change. So 2 things for every justification. So let's look at part B. Find the cyclist's acceleration at time t equals 45 seconds. Show the setup and the calculations for your calculations and indicate units of measure. Now, the acceleration is the derivative of velocity. And if I think it, I write it. So a of t is equal to v prime of t. Therefore, a of 45 is going to be v prime of 45. I want to be specific and not just leave t in there. So I want to make sure I'm putting 45 in. And now I'm going to go to Desmos and watch this. All I have to do is v prime of 45, and it will spit it out for me. So here we go. I'm going to record my answer, negative 0.10. I'm going to round to 5 and make that negative a little more obvious. So there's my acceleration, and then it wants units. So anytime I do a derivative, I'm going to take the meters per second, and I'm going to add a per time, or in this case it's time. So meters per second squared, or meters per second per second. Then it wants to know if the cyclist is speeding up or slowing down. So in order to know what's going on here, we also need to know the velocity. So I'm going to find the velocity at time 45. And the cool thing is Desmos will also do that for me. So I'm going to type in v of 45, and it's going to spit out the number, and I'm going to record that, negative 1.098 meters per second. And so now let's talk about how we know if the cyclist is speeding up or slowing down. Remember that velocity and acceleration have direction. So if they're both negative, that means they're both working in the same left direction. In other words, the cyclist is moving to the left, and the acceleration is then also pushing in that same direction. So if you're getting pushed in the same way that you're going, you're going to speed up. So in general, if the acceleration and the velocity have the same sign, that's when our particle or our object, or in this case our cyclist, is speeding up. When they have opposite signs, that means they're working against each other. So the velocity may indicate moving one way, but the acceleration is pushing in the opposite direction. That causes a slowdown of our object that's in motion. So here, we're going to say this. We're going to say since a of 45, we want to be specific, is negative, and v of 45 is also negative, the cyclist is speeding up. So velocity and acceleration have the same sign. All right, let's look at part C. Part C says find the distance between the cyclist's position at t equals 30 and their position at t equals 100. So we are going to be looking for the displacement here. So the distance between any 2 points in time is just how far you've moved. Now the little nuance here is that displacement can be positive or negative. Displacement will have direction. So for example, if the displacement is -5, we know that we've moved a net total of 5 units to the left. If the displacement is +5, we've moved a net total to the right of 5 units. So the nuance here is we don't want the displacement purely, we want the distance. And all that means is it's going to be the absolute value of displacement. So think of it like this way. I would never describe where I live as being negative 10 miles from target. I would just say I live 10 miles from target. So there's no direction. In other words, if we get a negative displacement, our final answer is just going to be the absolute value of that. So let's write down what we're going to do. In order to get displacement, we are going to do an integral. And we're going to go from 30 to 100. And we're going to integrate v of t dt. And we're going to see what is that. And Desmos will do that for me also. So I just need to type in int and then my limits of integration 30 to 120. Oops, sorry, 100. And then I'm just going to type in v of t dt. And this gives me my displacement, negative 96.858 meters. Now, to give the distance, now to take my final answer, I'm going to take this value and just give the absolute value. The distance is 96.858 meters. And that's the answer that I want to give. All right, final question here. Find the total distance that the cyclist travels over the time interval 0 to 120. Show the setup for your calculations. Now, total distance basically means how many miles did he put on his bike. So it takes any direction out. So essentially what we're doing here is we're going to look at the absolute value of our velocity curve. And all that's going to do is it's going to take any of those directions where I maybe moved in the left way and it's canceled out any movement in the right way. It's going to negate all that basically and say, well, you put this many miles on your bike. And the easiest way to do that in Desmos is just use the absolute value of velocity. And so my setup is going to look like this. I'm going to have another integral because I want total distance. And when I integrate velocity, I get meters. I get the change in position. So I'm going to integrate, but I'm going to integrate the absolute value of velocity. And when I type this into Desmos, it's going to be very similar to what I typed above. I'm going to go integral. And I'm going to have 0 to 120. But this time to get my absolute value, I can click that little icon down at the bottom, the little keyboard looking thing. And you'll see right above ABC, I've got the absolute value of A. So that's how I can get absolute value. I can also use my keyboard right above my enter key. I should have like a little vertical bar. So if I hit shift and then that button, I get the absolute value bars. So more than one way to access that absolute value. You can also type in the command ABS parentheses, and that will also pull up the absolute value. But here we get our total distance traveled, and we're going to write it down. It is 196.792 meters. And this will get me all the points that I need in order to answer this question. So let's zoom out, see the work. And this is a pretty straightforward, very classic particle, linear motion, cyclist, object moving around, velocity, displacement type question. And these are very basic skills that you should know. And so right now, let's kind of summarize what we just did, and let's take a look at some tips and tricks for how to do these types of linear motion questions. So in general, when we are looking at linear motion free response questions, they're pretty easy to recognize because in the problem, something is moving. Usually we're given some sort of velocity equation. We're asked about motion, direction, position, total distance, acceleration, position, things like that. They're just going to be a part of the problem, and they're very easy. It's very easy to tell if it's a velocity equation. So how do we approach it? Well, my first steps are going to start out with, if it's a calculator active question, make sure that you type the equation in its entirety into the calculator. Whether you're using a TI-84 and you go to Y1, take your time, type it in decimals. Don't forget to type it in as V of t equals, or whatever the equation is. Now, to find, when you're reading it, if you're given an initial condition or initial position, make sure that you record that on your paper, record the equation on your paper, and make sure that you're recording it correctly, especially with these digital hybrid exams. A couple reminders that V prime is your acceleration. So when you take the derivative of the velocity, that gives you your acceleration expression. Your position is going to be the antiderivative of velocity. So that might be something we want to add in here as well. So to go from velocity to position, you're going to use an antiderivative. And when you do that, you need to remember to solve for that constant of integration. So if ever you're asked to find an equation or an expression for the position, that's when you do the antiderivative. You have plus c, and you're going to use that initial position to solve for that c value. But this is only when you want an equation. For position. Okay, so other things that you're typically going to be asked for is potentially the displacement. So the displacement is kind of the net movement over an interval. So that's simply the integral from a to b of v of t dt. And remember, when we integrate a rate, anytime we do the integral, if velocity is meters per second, then when we do the integral, we turn into meters. So the units are going to shift, and anytime we integrate, we take away a per time, and anytime we do a derivative, we add a per time. So that's why when we see acceleration is going to go meters per second. So those units are going to shift every time we do a derivative or an antiderivative. Some other things you're going to be asked for is the total distance. That's a big one, and that's simply the absolute value. So on a non-calculator question, you might have to figure out where the velocity is 0, and then any negative values, you might have to set up more than one integral. Find the integral and the displacement or the distance traveled over any positive velocity spaces, and then any negative velocity spaces, you would take that integral and then take the absolute value of that, and then you can combine all those little sub-displacements, so to speak. We're often asked for a position. So if you're asked for a specific position in time, here's the formula that you want to remember. Your new position. So sometimes this position is after our known position, but your new position, we're going to call that time b, and that's going to be the upper limit of your integral. You're going to take your known position a lot of times they make it easy on you, and your known position is your position at time 0, but it's just your given position or your known position, and whatever that is, I always make that in this setup. It's your known position plus the displacement, and I always make sure that whatever time my known position is, that's going to be the bottom limit of my integral. And just remember, if your limits are ever kind of feeling backwards, so instead of going from 0 to 5, you flip them around and you end up going from 5 to 0, so like you're going back in time, it's okay. That integral will give you a negative displacement because you'll be moving backwards, and it'll all take care of itself. So just simply using the formula as it is going to get you that answer that you need. Now, you're also going to be asked to do a little bit of analysis about what's happening with the particle. So just a reminder that if the acceleration and the velocities have the same signs, that means that that particle is going to speed up. If they have opposite signs, that means that the particle is going to slow down. So how can you tell if you have positive or negative velocity? Well, you're going to want to show the value. So plugging the number in and getting a numerical value is always an excellent idea. So let's add that in. Try to show numerically whenever possible. But in case you can't show it numerically, if you ever have a graph that you can use, on a graph or in general, what we're going to look for is, so the velocity will be 0 at the x-intercepts, and then above the x-axis is where the velocity is going to be positive on a velocity graph. Below the x-axis, if you're looking at the graph of velocity, that's when your velocity is negative. And so positive velocity is generally indicative of moving to the right or forward. Negative velocity is moving left or backwards. And final reminder here, you're going to be asked probably at some point to know if a particle is changing direction. So it's really important to know that you need two things for a change in direction for linear motion. You need that velocity to be 0, and then you need to show a sign change. In other words, you need either on a graph, you need your graph to look like this. So if you have a velocity curve that looks anything like this, and this is t, and this is v of t, you're going to have a sign change here, but unfortunately right here, this is no change in direction. It is a spot where the velocity is going to be 0, but you'll see the velocity stayed negative. So there was actually no sign change or no change in direction that we can show. So the velocity being just 0 is not enough to show a change in direction. You need both the velocity to be 0 along with a change in sign to really prove that you've changed directions. So here are at a glimpse an overview of some tips and tricks for those linear motion free response questions. This is by no means complete. It's just very general based on kind of like years and years and years of looking at these. These tend to be the big topics that show up on this type of a free response. But no matter where you are with calculus, the more you practice, the more free response you're able to find and do, and Google some practice, the better you're going to get at doing these types of problems, and the more successful you'll be on the AP exam. But no matter what, just keep trying, and my encouragement to you as always is you've got this.